Welcome everyone. We have a very special ITC lunch today. First we heard an excellent ITC colloquium by Janna Levin over there, and if any of you has her book, you can get it signed. It's called Black Blues. I guess by now the blues turned into happiness after the detection of gravitational waves by LIGO, but she actually had the first copy of this book ready just on the day when LIGO detected it. So that was a prophecy. And Janna spoke about the interaction of a neutron star with a black hole and the possibility of getting an electromagnetic transient from that. This week is special because it's just before the elections. Next time we meet will be after the election. As you all know, that there is the information paradox about black holes, where it's not clear what happens to them if you throw information in. After they evaporate with Hawking radiation, they sort of lose it, and that's against the basic premise of quantum mechanics. But there is one exception to that. If you throw Donald Trump into a black hole, there is no information lost. In anticipation of what might be the first woman president, we actually have 4 women speaking at our ITC lunch today. The first is Bonaca. She's a new ITC fellow, and she will talk about 3D mapping of the Milky Way halo. She will be followed by Paola Caselli. I'm not sure if she's here, over there, from one of the directors at MPE, and she will talk about cosmic rays and the interstellar dust. And then we'll hear from Elisa Chisari from Oxford, that will speak about intrinsic alignments of galaxies from systematics to science. And finally, we'll hear again from Janna Levin from Barnard College, Columbia University, and she will talk about black hole blues. Anna.
Thank you. First we'll embark on the journey of mapping the Milky Way halo in 3D. And so the simplest motivation for embarking on such a journey is just to understand the place where we live, our own galaxy. But even more than that, measuring the halo shape of the Milky Way can point us to clues about how we actually got to where we are. So I want to motivate this a bit further with some nice work that Chirong Zhu did here at the CFA. And so what Chirong did was measure the halo shape in a high-resolution dark matter-only simulation as a function of radius from the distance from the center of the halo. And you can see that the triaxiality is pretty high throughout most of the halo, and then it drops slightly at around virial radius. However, when he looked at the same simulation that started with the same initial conditions, just included the influence of variance, he obtained a very different profile. So you can see that at large distances from the galactic center, the shape is similar to the one predicted by the N-body dark matter-only simulations. However, when you go closer in to the galactic center, the shape becomes more spherical. And so clearly measuring the shape as a function of radius would tell us not only about whether our cosmological paradigm is correct, but also how the different components of the galaxy interacted while the galaxy itself was forming. And so we want to measure the halo shape at larger distances from the galactic center. So luckily in the Milky Way, we have a lot of tracers in the stellar halo. So when we look at the map of the stellar halo in the Milky Way, we see that in addition to this diffuse component, we have a lot of this substructure that originates from tidally disrupting galactic satellites, such as dwarf galaxies forming the Sagittarius stream, and then to some very low mass accretion events, such as these very thin streams that were actually disrupted globular clusters. And these are the ones that we'll be focusing on in this talk. So I highlighted the polymer 5, the tightly disrupting globular cluster, and the GD1 stream, which doesn't have the progenitor anymore. It's completely disrupted. And we are focusing on these two cases because they are their disruption mechanisms are well understood, so we can model them and create models of these streams in different potentials and kind of see which ones fit the data. And to illustrate this point, I'm here showing some models of the polymer 5 stream in different halo potentials. So just looking at the projection on the sky and flipping between the spherical, the oblate, and the triaxial halo, we can definitely see differences. And this gives us hope that we can actually trace back what the shape of the halo is just by looking at some observed properties of these streams. And so a few years ago, I developed a method for modeling the streams and doing just that. And so when we applied it to the polymer 5 data, we got the following constraints on the halo shape. So I'm plotting here the axis ratios of x to y and z to y on x and y axis respectively. And so this is the posterior distribution obtained by modeling the polymer 5 stream. And so you might say, well, we have a solution. But if you've been following any news on the measurements of halo potential in the Milky Way, you might have heard very conflicting results. Anything from that the halo is spherical to oblate, prolate, and triaxial. And so the reason for that is that all of these measurements were obtained by looking at just a single stream, like we did here for polymer 5. So if we take another stream, the GD1 that we highlighted before, the results are now here shown in red. And so the contours go by half sigma, so the best fit models are indeed very different and kind of mutually excluded. So if we take the best fitting model of GD1 stream and create a model of polymer 5 stream in that potential, we get something that really does not fit the data shown in the white models. And again, if we do the same for the polymer 5 stream, for the GD1 stream, we obtain a model that is too long and asymmetric. It doesn't fit the observed stream positions. However, there is a small overlap region over here, which gives us hope that if we jointly model the streams simultaneously, that we will actually find a common solution. And so when we did that, there indeed seems to be the case that we have found some solution of halo shapes that fits simultaneously both the polymer 5 stream and the GD1 stream. And looking at the actual values, we can plot where the spherical halo is in this plot, and it seems to be excluded on the 2 sigma level. So to kind of tie it back to the plot that we started with, so here are the predictions in blue for dark matter only and in light blue for dark matter and baryons of how halo triaxiality changes with radius. And with yellow bar, I indicated the median value of the measurement obtained by fitting the polymer 5 and the GD1 stream. And it seems to lie exactly where it was expected in this one halo that Chirang analyzed. There is significant uncertainty, so the bar actually shows 25th to 75th percentile in our measurement. But there is a way forward. There are many more streams that could be used to be incorporated in this mechanism. And this is something I'm hoping to do here at the CFA. So on the observational side, one of the reasons that we only use polymer 5 and GD1 streams is that they are actually the only ones that have been followed up kinematically. So there is a lot of work observationally to follow up all of these streams that have been discovered in the Milky Way. And then on the theoretical side, also to build more flexible models, which actually will be able to capture the full complexity of the potential in the Milky Way. So keep tuned, and I'll take any questions. Yeah. You can probably rule out the Milky Way mass because then those things could move apart. Yes, that's very interesting. And I think goes in the direction of building more complex models of the potential, because really our potential model for the halo was just an ellipsoid, and we just changed the axis ratios. And it is very true that it is. That's not a very good approximation, and it is actually changing in time as well, because we have influences of both Sagittarius and the Magellanic Clouds.
When you do this modeling, do you need to know anything about the structure of the disrupted galaxy and its trajectory, and how much does that influence the... Right. So this.
So yeah, you do need to know about the structure of the progenitor, and that's why I'm focusing on globular clusters, because they're much simpler systems. So for dwarf galaxy, an issue is whether there was some rotation in the progenitor, and that would change the way it disrupts. In both cases, you do need to know some properties of the progenitor, where it was when it started disrupting, and so for the those are the parameters that we actually marginalize over in this scheme. But yeah.
I just had a technical question. How do you define halo triaxiality to one number?
Oh yeah. So it's if C, B, and A are the axis ratios, right, from shortest to longest, then the triaxialities. And like in the denominator, it's like 1 minus b over a squared divided by 1 minus c over a squared.
Question over there?
Yeah, I'm just curious, once you're done looking at all these streams, is there a way to measure the potential at the 1 kiloparsec scale, or are there measurements?
Oh. Yeah, I guess that's a good question. I really only thought about halo on larger scales, because it's where we would expect the dark matter to be more dominant. And it looks like even at 10 kiloparsecs, they are mostly dominated by the disk and the bulge. Yeah, but it does have very important implications for the dark matter detections. So yeah, I haven't thought much about it, other than, I guess, the kinematics of stars in the bulge.
Are you including moving groups of stars, which are maybe not necessarily streams, but some of them might be?
No, I haven't.
For a long time.
I haven't included them yet, but
Familiar with them, right?
yeah, it is really.
14 or some obscure name like that. Some of these things that were, I looked at these years ago, thinking that they might in fact be tracers of disrupted longer clusters. And that's never really been settled. But I think there are a fair number of these, so you might be able to add to this plot with a number of other.
And those would be mostly in the disk, right?
Well, they're high product motion, high velocity halo objects.
Right.
So they're probably not mostly in the disk.
Yeah, I think this shows to be a very we define a likelihood of observing a certain feature, and you can just add independent constraints from different objects, so it could definitely be incorporated. And I think the moving groups are probably fairly similar in this disruption mechanisms to what I've been looking at now. So.
Another point to keep in mind is, of
I haven't thought that much far away. It looks, yeah, I think people usually talk about the LMC actually having the mass that's similar to the one enclosed in the Milky Way, but yeah. But it also depends on what the mass of the Milky Way is, and which is, yeah, uncertain by a factor of 2, but yeah.
Question. Can you give us any feeling for why the effect of the baryons is greatest at 2 or 3 kiloparsecs, such that it produces almost spherical?
I don't think I'm the right person to ask. Yeah, I mean, I see what you're asking, but I don't know the answer to that question. Maybe someone in the audience who actually did the work. Yeah, I'm not sure how. So this is a caveat. This has only been done on one halo, so it is possible that there are like halo to halo variations here that just happened this way in this one isolated case.
Okay, I should put this on. Okay, so great to be here. So what I will talk about now is something that I have been interested since many years, and actually only recently, thanks to great collaborators and plasma physicists, we started to do a bit more into the detail this type of work. So this is, I just wanted to give you a little bit of the motivation first. So why I'm so interested in what cosmic rays do to interstellar dust. Well, first of all, we know that a lot of chemistry is going on, you know very well here, with Karen and other people. A lot of chemistry is going on ICES, on top of the surface of dust grains. And there have been also work in the past from, for example, laboratory work showing that the bombardment of for example, water ice on top of carbonaceous grains can actually provide say formation and form CO2, so the carbon dioxide molecule. And of course, the cosmic rays can inject energy in these dust grains, so they can heat them up. And if you heat them up, because the surface chemistry is exponentially dependent with the temperature, you can imagine that you can have a very interesting chemistry going on, at least as long as, say, the cooling time is not so short. But even in this instant or very small time, one can see the effects of cosmic rays. So here is just a picture coming from a paper from Eric Herbst that shows the various, say, processes that these dust grains in the interstellar medium can say, be affected by. So, of course, one is the cosmic rays. And they, of course, the cosmic rays, the good thing about them is that you have them all the way through the very densest part of dense cores, and even maybe in some part of the protoplanetary disk. Of course, there is a limit in the column density that they can penetrate, but these limits are quite high. We talk about 10 to the 26. Actually, this is something that is going now, some calculation that is going through in among these people here that you see the names, in particular Alexei Ivlev. So in any case, the cosmic ray you have all the way through the densest part of dense cores, and this is where actually stars and planets form. So we want to see how this can affect the composition of ices and energetics. And the other thing that is very important, then I'm done with the introduction, is the charging. So charging from cosmic ray for dust grains, it's as we have demonstrated from one paper that came out last year. It's very important, so it can change the distribution of charging on dust grains if you take properly cosmic ray into account. And it is important because, of course, the charging is linked to the, say, electron fraction, so ionization fraction in these cores, the dense cores in molecular clouds, where magnetic fields are, and then, of course, that can affect the dynamics. So the thing that was done as the first thing was the revisit this impulsive heating and thermal explosion of interstellar grains. That was done many years ago, but now with more knowledge about also the structure of the ices, we could do a little bit better. And so Alexei Ivlev, he's at Max Planck with me, and he's a plasma physicist, so he just went back to the Landau-Lifshitz and took the heat equation that described basically the variation of temperature in a reactive medium. So here the things to know are this QR. This QR is basically the energy that is released in, for example, if you have radicals that are combining, so if you have a reaction within the medium, you have to know the activation energies that are probably there when you have reactants in ice, for example. And then, of course, there are properties of the ice, like the various parameters that characterize, say, the solid. And this is the dimension parameter that has been changed in this paper here, 1, 2, and 3. You can do bidimensional or say three-dimensional. So this is just the starting point of the initial condition. So at time 0, when you consider like a dust grain and the cosmic ray coming, bombarding, say, the dust grain, we have assuming that you have some kind of delta function that is just, so you have like a spot heating in a very localized place. And what has been done here in this paper is basically put this equation in a non-dimensional form. So now theta is the equivalent of the temperature here in non-dimensional form, normalized by the activation energy, and then there is a dimensionless radius and time, which is now tau. Now, I don't want to bore you with all these details that you can basically look at in the paper, but one thing that this equation tell us is that there is one parameter, lambda, that basically depends on the, in a sense, in the chemistry that it's within the ice. That is the only parameter that basically regulate the fate of the ice. So just to make things short here, this is theta, so the temperature as a function of time for a case in which lambda is above or just below a critical value. So what Alexei found is that there are some specific values of lambda that are, say, above which you can trigger an explosion in the ice, depending, of course, also on the fraction of radicals that are present, and we can calculate them as well. So lambda, if it is just above the critical value, so the critical value is actually this 9.94 for the case where d is equal to 2, so we have this cylinder that we think is more appropriate for the penetration of cosmic rays within the ice. So we have this exponential growth, and you see that this can actually lead to, say, a flame front that is expanding, and that this can trigger the destruction and complete evaporation of the ice. If it is below this value, we have actually just a heat front that is propagating. So basically you have a heating of the ice, but the ice is going to cool down and form basically just you have evaporation of volatiles, etc. So the main point here, I just wanted to summarize here that we had in this paper, is that if you consider the cosmic ray spectrum, so consider the fact that about 10 to the minus 4 in, say, the abundance of iron nuclei in the cosmic ray flux is about 10 to the minus 4 compared to the hydrogen. So only heavy nuclei can actually trigger this explosion, and we measured basically how efficient is this explosion, considering a probe taking into account the ice composition. For the majority of the cosmic rays, these are the protons, what the protons can do is actually heat the dust, the ice, so the ice mantle, and of course also trigger some, say, first of all, mobility of radicals within the ice mantle, and then trigger some chemistry. So I don't know how much time I have now. I lost my, how much? Yeah, okay, wow, fine. So, but this is okay. I just wanted to give you then the some numbers here. So the desorption rates that, we also took into account the fact that cosmic rays, of course, can lose energy while they go through a molecular cloud, through losses, of course, in collisions with species. So taking into account all this, we have iron nuclei that can lead, as I said, explosions, and the desorption rates are actually similar to what one gets if we just have a heating of the grain at some, say, temperature that allow volatiles to go back. This is the whole grain heating, and also spot heating is something that has been parameterized and put in all the chemical models that we have. We also gave an upper limit on the basically product of the, just to the 30 seconds, product of the radicals, that is, must be less than 10 to the minus 3, so we give some constraints, say, on the fraction of radicals that have to be in these ices. And then this I have already said. So of course now I have no more time, and so I cannot tell you. I will try to tell you later, but let's see. I just wanted to tell you about the charging, but it's just if you give me 2 seconds. I know I'm going out the rule, but I don't know the rules. I'm here new. So here, the only thing I want to point out is that if you take into account in the charging of dust grains, also for example, the UV photons that are produced by cosmic rays when they propagate into dark media. So you have UV photons that can, of course, detach electrons from the grains. Taking into account these extra factors that were not taken into account before in calculations of the grain charging, Alexei, again, Ivlev, found that no, you don't have only negatively charged dust grains, but you can have a population of grains that are positively charged and also negatively charged. And of course, what this implies is that you can trigger the dust coagulation in regions of the cloud that not necessarily has to be large enough, because if you can imagine all the dust grains being negatively charged, so you have electrostatic forces to overcome that you don't, but if you have positively charged and negatively charged, you can actually put things together and maybe explain some of the results, observational results found around dense cores, where people have seen this core shine effect, where that can be explained only apparently if you have big grains. Okay, sorry, I'm late, I know. Thank you very much. I think... No, I'm not good in taking the say to take say on the how to say the typical things that goes on in other countries. Like in Germany, I'm not good at that. So yeah, this shows.
Question. Supernova 97A.
Uh-huh.
87A. Did show some dust later on the fall near the shore. And the question, of course, is that these cosmic rays that you are considering here also exist behind the shore of supernova remnants. And was their role in addressing dust formation incorporated? In other words, do they inhibit dust formation or change the properties of dust? Looked into that?
No, we don't. We have not looked into that. But yes, I mean, in this type of calculations, we are just for the moment considering, say, local type of interstellar, say, clouds. So we have, you consider cosmic ray ionization rates clouds that are that have ionization rates of the order of 10 to minus 17 or a few times 10 to minus 17. Of course, what we see here, if you go in an environment like nearby a supernova remnant where the cosmic ray ionization rates can go up by orders of magnitude, all these will be kind of multiplied. So I could see that maybe in these cases you have a large fraction of I don't know, like positively charged, for example, dust grains, or even, seeds of dust grains, which could prevent the, say, formation, or at least of the largest grains. But it's something, I have not touched, so that could be a nice problem, actually, to do. And then, of course, even the molecular clouds, say, nearby, they are exposed to these fluxes. They will see their ionization fraction, and maybe also the dust grain charging completely change, and that could change, could affect a lot, say, the dynamics, and maybe prevent the collapse, because you increase so much the ionization fraction that then everything is stuck basically along the line of along the region that is, say, exposed to these shocks. You have all kind of very large fraction of ions and electrons, and then it's very hard to then collapse and form maybe stars. But yeah, that's an interesting thought to explore.
Other questions?
Paola,
Hi, Phil.
how much do cosmic ray heating effects like these contribute to the typical temperature of dust grains in star-forming clouds, and would that temperature change in environments where you have less cosmic ray heat?
So the cosmic ray, so for the dust, I would say that it's not so important, because in fact, so either when you have dust with ice, either you have this explosion of the ice, or, for example, partial evaporation of the ice, and this cools down the dust grain very quickly. However, I think the crucial thing about the cosmic rays and the fact that they have, yes, a threshold, and this is shown, I know I'm not allowed, but it is shown here. You have a threshold, and now that has been calculated with high, say, accuracy, again, from first principle by one of the other people, Marco Padovani, who is now in Arcetri. So anyway, what you have is that, of course, the cosmic rays are influencing the gas temperature. So if you arrive at the point where you actually have some, say, drop-off of these cosmic rays, you can, of course, affect a bit the thermal balance, in a sense that the heating is not there anymore. There is no UV, there is no cosmic rays. You just have the cooling of the dust that actually cools down and can go probably very close to CMB, basically, because there is no way. So yeah, it's an interesting thing to consider, and probably this is very interesting in protoplanetary disk because you reach these points where the densities are so high, or say the column density are so high that cosmic rays have problems in penetrating. But for the dust temperature, I don't think that is a major issue or major problem because they are not very much heated, considering the cooling time that are really short. Sorry, yes. I should have prepared better. I should have tried once. Oh, my phone is on. So you now know all my secrets.
Okay. Thank you for having me. I'm Elisa Chisari. I'm a postdoc at University of Oxford, and today I'd like to tell you about the intrinsic alignments of galaxies. These are correlations between galaxy shapes across the large-scale structure that arise due to tidal interactions with that large-scale structure or preferential accretion along certain directions. And I want to focus on two aspects of this problem. So first of all, if you have correlations between galaxy shapes that are intrinsic in the large-scale structure, then you might imagine that this will lead to contamination, to weak lensing surveys. And this happens across all range of scales that you might want to probe. In the linear regime, we think there is a model that can describe these correlations very well, which involves relating the shape of the galaxy to the tidal field of the large-scale structure. In the nonlinear regime, this model doesn't work very well, so we have to improve on it. So I'm going to tell you about how to improve on the nonlinear regime using cosmological hydrosimulations. And on the other hand, I'm going to argue that since we know how these correlations behave on the linear regime, we can try to extract cosmological information from them. So to characterize alignments in the large-scale structure in the nonlinear regime, I use the Horizon AGN simulation. This is a cosmological simulation of 100 megaparsec over h. And it has full baryonic physics included, so AGN feedback, supernova feedback, stellar winds are included. Those are the typical parameters of the simulation. So galaxies are formed, we can identify them, classify them, and we can measure their shapes. And I'm going to focus on the minor axis orientation of that shape. And one point in favor of using hydrosimulations to characterize intrinsic alignments is that there we can actually measure the alignments in 3D, while in observations we measure them in projection. So we can measure correlations of the minor axis and the separation vector between, say, for example, dark matter particles in the left, or the separation vector between galaxies on the right. And what we find from the simulation is that at low redshift, the signal in the intrinsic alignments is dominated by elliptical galaxies that point towards each other. And that is consistent with what we observe in galaxy surveys right now. We can also see that if we look at low luminosity galaxies, those low luminosity galaxies are pointing radially towards other high luminosity galaxies. We also see that the location of those low luminosity galaxies is preferentially along the direction of the major axis of a higher luminosity galaxies. So anisotropic clustering is also contributing to this alignment signal. We can trace the evolution in redshift of this signal, and we see that the alignment of ellipticals increases towards low redshift from the red line at redshift 3 to the violet line at redshift 0. We can also see that the disks in the simulation have little to no alignment at low redshift, and that's the cyan line. And as we go to high redshift, we find a tentative signal of disk alignments being present in the simulation. And this has the opposite sign to the alignments of ellipticals, which means that disks are oriented tangentially around over densities in the large-scale structure. And finally, we can do this in projection as well, so we can probe, we can see how the projected shapes of galaxies correlate with the density field, and this it is possible to compare it directly to the observational constraints. So here I'm showing what the projected signal looks like for very luminous galaxies as a function of redshift. And with this, we can try to extend the tidal alignment model to nonlinear scales. And if you want more details, please ask me later or go to the paper. Okay, so in the linear regime, the situation is a bit different. So in the linear regime, we know that there is a model that works very well to describe these correlations. So at this point, we're ready to use it for extracting cosmological information from this model. And so the first equation up there shows that the shape of a galaxy is a bias parameter times the tidal field at linear order, and then some additional terms that come in at higher order. So for example, the term here is the next order term, which quantifies the response of a galaxy to a simultaneous change of the density field and the tidal field. And so if the universe is Gaussian, then on linear scales, we will only have the contribution from the first term if we're trying to measure correlations between density field and galaxy shapes. But if there is significant non-Gaussianity, then the second term will start contributing. And that can happen on nonlinear scales due to the nonlinear processes of galaxy formation and evolution. But it can also come in on large scales due to primordial non-Gaussianity. And in particular, there are different models of inflation that predict contributions to such term. So for example, if we write down the squeeze limit bispectrum of the primordial potential, there are models in which this bispectrum depends on the angle between the short wavelength mode and the long wavelength mode. And this would be an anisotropic kind of non-Gaussianity, so the anisotropic analog of what we're used to think of as FNL. And this anisotropic analog would change the power in the tidal field and give you a different alignment signal. These are the current constraints on this anisotropic parameter, anisotropic non-Gaussianity parameter from Planck, from temperature, from the temperature of the CMB, from the correlations. And so in this alignment model, what you get in the presence of anisotropic non-Gaussianity is a large-scale effect. So if that factor in parentheses is the tidal field, this is the bias parameter that quantifies the response of a galaxy to the tidal field, and that's the matter power spectrum. And so what you can see here is that you have that linear component, yes, so the response of the galaxy shape to the tidal field in a Gaussian universe, but then you get an additional scale-dependent bias, which is proportional to this A2 parameter, and that goes as 1 over k squared. So this is basically the analog effect of FNL, but now seen on the correlations of galaxy shapes. And one can ask, how well can we constrain this from future surveys? So imagine that you select elliptical galaxies in your survey and you measure their shapes, and you want to know how well you can constrain the anisotropic non-Gaussianity parameter. So that's the y-axis. You can see a sub 2 on the left, but then a sub 0 is basically 4 times FNL, so this is the other non-Gaussianity parameter that we're used to. And these two are degenerate, so we have to constrain them at the same time. So if we use one red galaxy, one sample of red tracers, then these are the type of constraints that we get. But we can even improve that by using a combined probe analysis. So we can use, instead of just restricting to the sample of elliptical galaxies, which we know have alignments, we can use blue galaxies as well. And moreover, there is an effect that changes the orientation of the isophotes of the galaxy. So if you measure intrinsic alignments for galaxies using different isophotes, you get different answers. And that's because different regions of a galaxy are responding differently to the tidal field. So you can even use that as additional information to try to constrain this parameter. So what I'm showing here is a progression of how the parameter constraints improve as you add different tracers of the large-scale structure. So the top left panel is what I showed you before. Then you add a second tracer, a second shape measurement for the red galaxies. Then you add the blue galaxies to help with the degeneracy with FNL. And finally, you add the cross correlations between the blue sample and the red sample. And eventually, with Euclid, we might be able to get to a 1 sigma error bar of around 50, which you can see is comparable to what Planck has to offer at this point. Okay. So just to summarize, I told you about two aspects of the intrinsic alignments of galaxies. One of them is that we don't know very well what the alignments are doing in the nonlinear regime, and we need to for future surveys if we want to learn about dark energy from weak lensing. But we're learning to model them with the help of cosmological hydro simulations. And then on the other hand, on the linear regime, we have enough information on these alignments from current surveys and from the simulations that can help us use them as a source of cosmological information. And in particular, we could constrain an isotropic non-Gaussianity from two-point correlations, which is not true from the clustering, for example. Okay, thank you.
There is one aspect of this problem that could be complicated, and that's the fact that we are looking at the luminous parts of galaxies, and that's the baryonic matter. And the baryonic matter, in principle, can exchange angular momentum with the dark matter halo. And exactly how it makes the disk or the bulge, whether it does it by clumps falling in or cooling that is smooth or some cooling flows or whatever, can affect the exchange of angular momentum with the halo. So the question is, how robust do you think is our understanding of whether the angular momentum of the baryons actually reflect the angular momentum of the total mass in a galaxy?
Yeah, so that's a very good question. So right now what we're doing is we're analyzing the shapes and angular momentum of the dark matter halos and comparing them to how the alignments of these galaxies evolve in the simulation. So we'll have a direct answer to your question in a couple months. Yeah.
What about contamination from substructure?
Yes.
In other words, one big halo can have one big halo within a host. Can
Yes.
actually drive the angular momentum vector in a different direction.
Yeah, so that's a very good question. So it depends. So basically, depending on how you select the galaxies in your simulation, how you identify the halos, you can have some biases on very small scales. But the scales are really, really small, and we've seen that changing or way to select this substructure doesn't change the results very much. Is that what you were pointing out? Yes?
More.
Any other questions? No? Over there? Yes. Go ahead.
So the fact that the elliptical galaxies show a signal of alignments and the disks not, is that just a statement of mass, or is it something else that makes the disk align whatever?
Right. So we think that there are two mechanisms going on to align the galaxies. So for the if you talk to a theorist, so for the elliptical galaxies, the idea is that the tidal field is stretching these galaxies in preferential directions. In reality, what we see in simulations is that probably this also has to do with the preferential accretion and merger of the galaxies along the direction of the nearby filament. So essentially what you have is that the disk galaxies that live in the filament are aligned by tidal torques acting from the large-scale structure. So they align their spin with the tidal field via these torques. As the disk galaxies are falling into denser environments, there is eventually a mass transition over which the mergers become important, and they switch to these other alignment mechanisms that the ellipticals have. That's what we see, at least in the simulation. Yeah.
Thank you very much.
Thank you.
So this is my third talk in 3 days here. I hope some of you aren't completely sick of me. Oh, sorry, I have to actually start my presentation. And I'm not going to stop. I'm just going to keep talking for the next. Because this is the third talk I'm doing, I thought I would discuss work very much in progress. This is not going to have a conclusion at the end. There's not going to be a takeaway, or this is just sort of things I've been thinking about with students and postdocs. Your very own Dan Durazio, who's now a postdoc here, has been working with me on this project. So we were thinking about charge on black holes. And I think one of the interesting things that happened as I started to think about electromagnetic properties with black holes is that basically I had a lot of wrong ideas that were foisted on me as standard lore on the story of black holes. One is that black holes can't support magnetic fields, and the other is that charge is never going to be interesting for a black hole, because if a black hole has charge, there's such a huge reservoir charge in the universe that it will instantly discharge, basically, has been the argument. And neither of those two statements that I just made are actually correct, I don't think. So I wanted just to discuss this idea of charging up a black hole and to tell you what we've been thinking about. And that is mostly has to do with charging up a black hole in the presence of an external magnetic field. And that is a very interesting situation if a black hole is near a highly magnetized neutron star, for instance, which is what I spoke about earlier, electromagnetic circuits that form when the black hole is in the presence of a highly magnetized neutron star. But let's forget about the electromagnetic circuit for a second and just pretend that there's a black hole in an external magnetic field and that the external magnetic field is not negligible. It's 10 to the 12 Gauss, something like that. Okay, so I know that not everyone likes to think in terms of this pure relativistic language, but I promise to go through these next two slides so quickly that nobody in the room will understand it. So we're all going to be on an equal footing here. I started to think about this more with a paper by Bob Wald, which might be the most beautiful paper I've ever read. It's a 1974 paper. It's like 4 or 5 pages long. It's absolutely stunning, where he finds an exact solution to Maxwell's equations in the presence of a spinning black hole in a uniform B field. So how does he do it? So let's just very quickly start. We have F mu nu, the Maxwell tensor, which describes the electromagnetic fields. It is the antisymmetric derivative on the 4-vector potential, and in vacuum, that's Maxwell's equations, is just taking the derivative of F mu nu, which is basically taking the derivative of the E and B fields. Okay, so if we consider a black hole that's spinning, the space-time of a spinning black hole has a lot of symmetries. One is that it's axisymmetric, and if you like to think in 4-vector notation, that means that there is a vector which points in the axial direction, which will be special. And it's stationary, which means that there's a vector that points in the time direction that's special. So it's not static because it's spinning, but it is stationary. And if you like Killing vectors, you can find out that these are solutions to Killing's equations, which is nice. And that will turn out to be important on this next slide, which I'm going to do very, very quickly. If I take the derivative of Killing's equation, which is just a symmetric derivative on this vector, you can rewrite it and do some fancy permutations, see how fast I'm going. Nobody's understanding it. In a vacuum spacetime, I'm allowed to permute the derivatives. Great, black holes are actually vacuum spacetimes. I look at the second term and I realize that it's 0 by Killing's equations, and I very quickly come to this conclusion, bang, 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 that the second derivative of these Killing vectors is 0, and that is just Maxwell's equations. Okay? So super quick, just to say that because of the symmetries of the space, just summarizing, Wald immediately writes down the electromagnetic solutions must be sums of Killing vectors. It's really beautiful. He knows the E field and the B field automatically because he knows that the 4-vector potential must be a sum of psi, the axial Killing vector, and eta, the time-like Killing vector. Now, he chooses these coefficients where B is the magnitude of the external field, A is the spin of the black hole, M is the mass of the black hole. He chooses those coefficients by deriving the charges that the black hole would have due to each and making them cancel. So what does this mean? That is an exact, beautiful solution to the electromagnetic fields around a spinning black hole when the black hole is uncharged. Okay, that's what Wald finds. Okay, now, even if you didn't follow all of that, I just like to show it because it's so beautiful. What it really means is what we have is a black hole distorting the magnetic field that it's immersed in and creating electric fields because of its spin. And it's it's torquing up the magnetic fields and creating these electric fields. Now, because it's created an electric field, Wald realized, well, that means that charges are going to start to accrete onto the black hole. And he makes this very simple argument that even though it starts uncharged, it will, if there's any reservoir charge, begin to accelerate charges. Let's just think Newtonian for a second. You know, the force on the charged particle is the combination of the electric and magnetic fields. And if there's a component of E along the B field, it'll drag charges in, spiraling along these B field lines, and they'll accrete onto the black hole. Now, oh, sorry, that was supposed to show up later. Pretend you can't see that. Charges will flow along the field lines into the black hole, and Wald argues, he finds that at this value of the charge, in these geometrized units, twice the magnitude of the magnetic field times the spin of the black hole, that at that value, the black hole will stop accreting charge, that it's actually energetically favorable for charge to accrete onto the black hole until that value of the charge. Now, this is a famous argument, again, in this beautiful paper, but I actually am now taking issue with this argument. I won't go into all the details, but Wald, when he solves for it, only finds the energetic favorability of accreting charge along the poles. And he's clear that he only found it along the poles. Now, people have argued it's true in general, but it's not true in general, I don't believe, because if you look at E dot B, which drives charges along the field lines into the black hole, it is simply not zero off the poles. And so it looks like it will be able to pull charges in along other areas. So let me just show you a quick picture. This shows, sorry, let's go back. Let's see if I can stop it. This shows the E dot B and the E fields and the B fields. So let's see which are which. The red are the B fields, the blue are the electric fields, and E dot B is color-coded to be, you know, positive or negative with this kind of a scale around the black hole. So this is for an uncharged black hole. You see that there are electric field lines pointing into the black hole, which will drag in charge. And now let's see if this runs. Nope, one more time. There it goes. And as it charges up, that distribution of E dot B changes around the black hole. And at the Wald charge, whoops, I wish I had stopped it too. I'll let it run again. At the Wald charge, you can see, which is, we're just slightly shy of it in this 1.999. Oops. Okay, it doesn't like to stop on that slide. Sorry. So you can't see it. On the Wald charge, it's true that E dot B is zero along the poles, but it's still not zero everywhere else. So our question is, our question is, will it reach the Wald charge and then begin to discharge, and then reach the Wald charge again, and then begin to discharge? And so will it be a constantly fluxing system? This is something we're asking, which I think would be extremely interesting. Now, I think I'm almost at the time. I tried to do these numbers this morning for what charge we were talking about. And I'm not going to stake my life on these numbers right now, but I get a huge number of coulombs for if it's submerged in a B field of 10 to the 12 Gauss. And let's assume that that B field is due to a neutron star, so that I let the B field drop off as 1 over r cubed as, with its distance from the neutron star. But yeah, it's a lot of charge. So it could be very significant if it does acquire this much charge, even if it is suppressed by 1 over r cubed. Now, let's see what this means in terms of the no-hair theorem. So the no-hair theorem is usually expressed as the statement that a black hole simply cannot support any magnetic fields. All magnetic fields are a form of hair. That's somehow I got this message as a student. This is false. Actually, what the no-hair theorem technically states is that a black hole cannot support any magnetic fields in vacuum, obviously, that are not consistent with a monopole of electric charge. So once I charge up this spinning black hole, it creates its own B field. And you can see that it must, because I know that if I co-rotate with that black hole, it only looks like a charged particle. And I'm going to be less sensitive to the fact that I'm running over in time. It only looks like a charged particle with no B field, and we all know that E and B fields, mix under Lorentz boost, so if I'm not co-rotating, I must see a B field, and it's pretty intuitive that a spinning monopole creates a magnetic field and it creates a dipole field. So our other question is, regardless of this issue of the wall charge, is while it has charge on it, I mean, regardless of this fluxing issue, will the black hole then have a significant magnetic field? And will it be able to create basically its own kind of pulsar, is one of the questions we're asking. Okay, thank you very much.
Janna, aside from a charge, there could be currents in the system. In other words, perhaps the particles that you alluded to, that the charge can suppress inflow in other directions, is that there is sort of a circuit that charge flows from one point to another.
Yeah. I think that putting in the actual charges would be very interesting to see how they actually flow. Right now we're kind of hypothesizing that at infinity we have a magic reservoir of electrons and positrons, so we don't worry about the differences between protons and electrons and things like that. And just, abstractly, what would it do if it could? Now, in reality, there will be currents, as you say, and if it really is coming from a neutron star, the reservoir of charge, then it's coming from a certain angle, and that creates a certain flow, and that would change the story. Also, as we discussed earlier, if these E fields get big enough, there will be dielectric breakdown of the vacuum anyway, and it will start to make its own charges, E plus, E minus pairs. So all of this is, I think, could be quite, rich with possible consequences.
If it generates its own pulsar, like behavior, that means that there will be a derivative to the spin of the black hole. Do you know how long it will take until the whole thing radiates away?
Can't we say that from pulsar spin down? Could we make an analogy with the pulsar spin downs to guess that? I would imagine it's not incredibly fast. But that would be my intuition, is that I would compare it to pulsar spin down. Yeah.
It would be interesting if all of them you expect to have zero spin today because they radiated away very quickly.
Yeah, I mean, I think it would have to be very quick, because it would only be when it's very close to a neutron star, let's say, or something like that, that it would acquire significant charge, because that's the only time that the B fields are strong enough to acquire significant charge, and that's a short period of time that it gets in that close because of the merger under, gravitational merger. So, I mean, it would be interesting in, I'm sure, many other settings where there are magnetic fields around black holes in general, and I'm sure that this is part of the supermassive black hole story with magnetic fields on it. Which is again, I just think if it pans out stably, that it's rich with possible implications in different settings. Other questions?
No more questions. I wanted to mention that this was a unique session in the sense that we ended on time. And that the fact that we had women speakers. More often in the future.
Thanks so much.
I was remembering when looking at that movie.
Thank you.